Welcome to this webinar by Applied Parallel Computing. I'm Juraj and I will present you advanced aspects of CUDA. Knowing the underlying architecture is essential in order to fully utilize the GPU compute units. The best results are obtained when all the available hardware is computing something. Otherwise, the resources are wasted. We have different hardware resources in different architectures. We will talk about the latest three architectures that are Fermi, Kepler and Maxwell. We will look at their characteristics and some specific features of these architectures. Other essential knowledge in order to efficiently use CUDA is the memory hierarchy. Memory latency is usually the most limiting factor in terms of time consumption, especially in memory-intensive operations. We will focus on those aspects of memory hierarchy that are accessible by CUDA programming model. Therefore, you, as a programmer, can make an advantage of these features and further speed up your code. In this video, you will learn about shared memory, that is low latency memory that can be used to cache your data and avoid expensive accesses to global memory. Efficient data transfers are closely related to memory system. Amount of transferred memory and the data communication path during the transfer have severe impact on the application performance. We will also introduce the concept of CUDA streams that is necessary in order to utilize simultaneous kernel launches within a single GPU or overlap communication with computation. And finally, we will introduce some debugging and profiling tools. During the project lifecycle, the code might grow huge, or you may be dealing with code from a new project you are not familiar with. In such scenarios, it would be useful to have supporting tools that help you understand the code base, know where the bottlenecks are, and so on. We will introduce tools such as CUDA GDB, CUDA Memcheck, and NVIDIA Visual Profiling tool. Let's have a look on architecture of CUDA-capable GPUs. The choice of the execution units number, their latency and throughput, is a central microarchitectural design task determining performance of the chip. Understanding the basic architecture of whatever system you are programming for is necessary in order to create high-performance applications. Most desktop systems consist of large amount of system memory connected to a single CPU, which may have 2 or 3 levels of fully coherent cache. GPU memory hierarchy is in many ways similar. Typical system memory for CPU nowadays ranges anywhere from 6 to 64 GB of system memory for the highest-end workstations. This system memory is connected to GPU via PCI Express with bandwidth of 8 GB per second, in case of PCI Express of second generation supported in Fermi. Third generation PCI Express doubles this bandwidth to almost 16 GB per second. Note that the GPU has its own memory on board, that is of course global memory. Global memory size can be anywhere from 700 MB all the way up to 12 GB in case of Tesla K40 or 24 GB memory in Tesla K80 model. As you see, the trend is that GPUs don't have as much memory as CPUs, but the memory bandwidth for GPUs is usually substantially higher than that of even the highest-end CPUs. Global memory bandwidth reaches 200 GB per second with latency of 4 to 800 clock cycles. All modern CUDA-capable cards, meaning Fermi Architecture and later, have a fully coherent L2 cache. As with memory, the GPU's L2 cache is much smaller than a typical CPU's L2 or L3 cache, but has much higher bandwidth available. Latency of L2 cache is around 100 clock cycles. There is one L2 cache on chip, divided between streaming multiprocessors as needed. Finally, there is the L1 cache. High-end NVIDIA graphic cards have multiple streaming multiprocessors, and each is equipped with its own L1 cache. This memory provides low latency access, about 10 to 20 cycles. Other difference from CPU is that this fast L1 memory in GPUs can be programmable, or at least some portion of it, known as shared memory. We will talk about shared memory later in this video. In CUDA programming model, the specific hardware architecture is identified by compute capability. The compute capability of a device is represented by a version number. This version number identifies the features supported by the GPU hardware and is used by application at runtime to determine which hardware features or instructions are available on the present GPU. The compute capability version consists of major and minor revision number. Devices with the same major revision number are of the same core architecture. The major revision number is 5 for devices based on the Maxwell architecture, 3 for Kepler architecture, 2 for Fermi, and finally 1 for devices based on Tesla architecture. The minor revision number corresponds to an incremental improvements to the core architecture, possibly including new features. Compilation directives allows us to specify the target architecture. Source files compiled with NVCC compiler usually consists of mix of host code, that is code that executes on the CPU, and device code. CUDA compilation works in a way that CUDA device code is separated by CUDA frontend, replaced by a set of CUDA runtime function calls, and passed to standard C/C++ compiler. But what happens with the device code? It is of course compiled by NVCC. Depending on the value of the NVCC flags, this device code is translated by CUDA compilers into binary, represented by Cubin object, or into intermediate pseudo-assembly PTX code. Binary code, represented by Cubin object, is architecture specific. A Cubin object is generated using the compiler option code that specifies the target architecture. For example, compiling with code equals sm_20 produces binary code for devices of compute capability 2.0 of Fermi Architecture and devices like Tesla C2075. Binary compatibility is guaranteed from one minor revision to the next one, but not on the previous minor revisions or across major revisions. In other words, a Cubin object generated for compute capability 3.5 will execute only on devices with the same major revision number, that is only on Kepler architecture, and with minor revision number that is equal or greater than specified compute capability. The virtual architecture specified by arc option, in our case for example arc equals compute_20, determines what type of PTX code will be generated. PTX code loaded by an application at runtime is compiled to binary code by the device driver in case of no compatible binary object was found. This is called just-in-time compilation. Just-in-time compilation increases application load time, but allows the application to benefit from any new compiler improvements coming with the new device driver. Specifying arc option helps compiler to make presumptions about architectural features and generate more optimized PTX code than that default option that assumes compute capability 1.0. As you can see in this example, you can specify multiple target architectures of your application. One advantage of including multiple virtual architectures, that is multiple versions of PTX code, is that you have executable compatibility with a wider variety of target GPUs, and your code will be better optimized for such target architectures. An advantage of including multiple binary GPU targets is that you can avoid just-in-time compilation step, in case the GPU with a specified compute capability is present. One possible disadvantage of specifying a lot of these options is code size bloat. Another possible disadvantage is compile time, which will be generally longer as you specify more options. You can find CUDA compute compatibility table under this link. It will give you information about architecture and compute capability of your NVIDIA GPUs. We will start our architecture overview with Fermi. Fermi, produced in 2010, features 3 billion transistors distributed within 16 streaming multiprocessors and control logic, reaching peak performance in floating point of 1.5 teraflops. Fermi supports up to 6 GB of DRAM memory thanks to the 64-bit addressing capability. DRAM bandwidth reaches 192 GB per second, and there is also an L2 cache on chip with capacity of 768 KB. Other subsystems on chip are host interface, gigathread global scheduler, and DRAM ports that connect to global memory. Host interface connects GPU to host via PCI Express of second generation. This transfer reaches peak performance rate of 8 GB per second. Notice the disproportion of the link between the global memory and host interconnect. You should adjust frequency of memory transfers according to this hierarchy. That is, in ideal case, you minimize host device transfers and rather store intermediate data in global memory when you can access it more often as needed by an algorithm. However, global memory is also not appropriate for memory-intensive operations. In such cases, you should use low latency and high bandwidth shared memory that we will discuss later. Gigathread Global Scheduler distributes thread blocks to streaming multiprocessors and its thread schedulers, and manages the context switches between threads during execution. As you know, in CUDA programming model, the thread block is an abstraction of streaming multiprocessor, and other abstractions in CUDA are grid of blocks that corresponds to GPU and thread that corresponds to a single CUDA core. Let's have a closer look on the streaming multiprocessor. Each streaming multiprocessor in Fermi features 32 single precision CUDA cores, and each core consists of integer and floating point unit. Floating point unit implements the IEEE floating point standard, also providing the fuse multiply of the instruction. Load store units allow source and destination addresses to be calculated for 16 threads per clock. Special function units execute transcendental instructions such as sine, cosine, and square root. When it comes to workload scheduling, the Gigathread Global Engine schedules thread blocks to various streaming multiprocessors. Further workload distribution is done on individual streaming multiprocessor level. Each streaming multiprocessor contains dual warp scheduler, where each warp scheduler distributes warps of 32 threads to its execution units. Execution unit is one of the 4 columns, 2 16-core execution units, 1 unit of 16 load store blocks, or execution unit of 4 special function units. Each streaming multiprocessor features 2 warp schedulers and 2 instruction dispatch units, allowing 2 warps to be issued and executed concurrently. Each streaming multiprocessor contains on-chip memory that can be used either to cache data for individual threads, L1 cache, or to share data among several threads, that is shared memory. Shared memory enables threads within the same thread block to cooperate, enables extensive reuse of on-chip data, and greatly reduces off-chip traffic. Each streaming multiprocessor has 32,000 registers. The maximum number of registers that can be used by a thread is limited. In Fermi Architecture, the limit is 63 registers per thread. The number of available registers degrades from 63 as the workload and resource requirements increases by number of threads. Kepler Architecture, produced in 2012, consists of 7 billion transistors distributed within 15 streaming multiprocessors. While the goal of the previous architecture was focused on increasing pure compute performance, the Kepler architecture focuses also on the energy efficiency and programmability. Today, the primary constraint on processor performance is the power consumption budget. Having a more efficient process enables us to add more processing cores, thus increasing performance. Kepler achieves 6 double precision gigaflops per watt, while Fermi achieves only 2 in high-end NVIDIA GPUs. Global memory characteristics remain the same as in the previous architecture. The Kepler GK110 GPU features 1.5 MB of dedicated L2 cache memory that doubles the amount of L2 cache available in the Fermi architecture. Kepler introduces new version of PCI Express that doubles the bandwidth of second generation used in Fermi. Kepler also introduces new technologies such as HyperQ, dynamic parallelism, or GPU Direct. HyperQ increases number of hardware work queues from 1 to 32, which enables multiple CPU threads or processes to launch work on a single GPU simultaneously. Having a single work queue meant that Fermi could be underoccupied at times, as there wasn't enough work to fill every streaming multiprocessor. By having 32 work queues, Kepler can in many cases achieve higher utilization by being able to put different task streams on what would be otherwise idle streaming multiprocessors. GPU Direct allows communication to directly exchange data without needing to go to CPU system memory. The DMA feature in GPU Direct allows third-party devices such as SSDs or network card adapters to directly access memory on multiple GPUs within the same system, which significantly decreases the latency of MPI messages to or from GPU memory. Dynamic parallelism allows threads to launch other kernels, which can simplify programming your application in some cases. The Kepler architecture employs a new streaming multiprocessor architecture called SMX. Kepler reduces the amount of control logic and increases the number of CUDA cores 6 times when compared to Fermi streaming multiprocessor. Because all the Kepler CUDA cores run at a lower clock speed than in Fermi, the GPU as a whole uses less power even though it delivers more performance. Primary focus was put on energy efficiency, resulting in fact that 2 Kepler CUDA cores consumes 90% power of a single Fermi CUDA core. One of the design goals for Kepler was to significantly increase the GPU's delivered double precision performance, since double precision arithmetic is in heart of many high-performance computing applications. Kepler SMX also retains the special function units for fast approximate of transcendental operations, providing 8 times more special function units as the Fermi streaming multiprocessor. Each streaming multiprocessor features 4 warp schedulers and 8 instruction dispatch units, allowing 4 warps to be issued and executed concurrently. Kepler's quad warp scheduler selects 4 warps, and 2 independent instructions per warp can be dispatched each cycle. Compared to Fermi, only 2 warps could be issued and executed concurrently. Maxwell, released in 2014, consists of 16 streaming multiprocessors divided into 4 graphics processing clusters, reaching performance of 12 double precision gigaflops per watt, making computation even more energy efficient than previous architectures. Host interconnectivity is implemented by PCI Express of 3rd generation, and L2 cache has grown to 2 MB. Having a larger cache reduces the number of memory requests that have to be made to global memory. Maxwell increases the maximum active thread blocks per streaming multiprocessor from 16 to 32. This should help improve occupancy of kernels running on small thread blocks, such as 64 threads per block. Kepler introduced large improvements to the performance of atomic operations to device memory, but shared memory atomics used a lock, update, unlock pattern that could be expensive in case of high conflicts for updates to particular locations in shared memory. Maxwell introduces native shared memory atomic operations for integers and native comparence swap, which can be used to implement other atomic functions with reduced overhead compared to Fermi and Kepler methods. Maxwell has decreased number of CUDA cores in streaming multiprocessor to 128, which aligns with warp size. Having a core count be multiple of a warp size makes it easier to utilize efficiently all CUDA cores. Savings are made also in terms of area and power that had to be spent to manage data transfers in more complex organization used by Kepler. Maxwell further improves on Kepler by separating shared memory from L1 cache, providing a dedicated 96 kilobytes of shared memory in each streaming multiprocessor. The per thread block limit remains 48 kilobytes also in Maxwell, but the increase in total available shared memory can lead to occupancy improvements. Dedicated shared memory is made possible in Maxwell by combining the functionality of the L1 and texture caches into a single unit. Each streaming multiprocessor contains 4 warp schedulers, and each warp scheduler is capable of dispatching 2 instructions per warp every clock cycle. Compared to Kepler scheduling logic, a number of improvements in the scheduler were integrated to further reduce redundant recomputation of scheduling decisions, improving energy efficiency. We have seen how GPU architectures evolved, optimizing its performance and energy efficiency. Here you can see a short summary of the architectural features we have talked about in this section. In the following part, we will have a closer look on shared memory and how to use it efficiently to improve performance of your applications. In this part, we will inspect properties and usage of shared memory. When you port applications to CUDA, you probably expect a massive speedup compared to a serial CPU code. Provided that you adhere to good CUDA programming practices, such as coalescing memory accesses or avoiding code divergence, and you still don't reach good speedup, you probably want to inspect memory access patterns of your application. We have seen that memory transfer between host and device is done at 8 or 16 GB in best case. We will see that PCI Express can be shared among multiple users or peripheral devices, therefore the bandwidth can be even more reduced. Memory access to global memory has bandwidth reaching 200 GB per second, while on-chip shared memory has bandwidth 1600 GB per second and much lower latency. Because it is on-chip, shared memory is much faster than local and global memory. In fact, shared memory latency is roughly 100 times lower than uncached global memory latency, provided that there are no bank conflicts between the threads, which we will examine later in this section. On Fermi and Kepler devices, each multiprocessor has 64 kilobytes of on-chip memory that can be partitioned between L1 cache and shared memory. We are talking about this part of memory hierarchy, with CUDA cores being somewhere here. For devices of compute capability 2, there are two settings, 48 kilobytes shared memory and 16 kilobytes of L1 cache, and the other way around. Devices of compute capability 3 and later allow the third setting of equal distribution of 32 kilobytes shared memory and 32 kilobytes of L1 cache. By default, the 48 kilobyte shared memory setting is used. This can be configured during runtime using API function. As we have seen in Maxwell Architecture, shared memory is separated from L1 cache, providing a dedicated 64 kilobytes of shared memory in each streaming multiprocessor. Shared memory is allocated per thread block, meaning that all threads in the same block have access to the same shared memory. Threads can access data in shared memory loaded from global memory by other threads within the same thread block. When sharing data between threads, we need to be careful to avoid race conditions. While threads in a block run logically in parallel, not all threads can execute physically at the same time. To ensure correct results when parallel threads cooperate, we must synchronize the threads. CUDA provides a simple barrier synchronization primitive, _sync threads. A thread's execution can only proceed this barrier after all threads in its block have reached this point. In this example, we will compare performance of reduction in global memory and its modification that uses shared memory. Shared memory in CUDA C device code is declared using the shared variable declaration specifier. There are multiple ways to declare shared memory inside the kernel, depending on whether the amount of memory is known at compile time or at runtime. If you know amount of shared memory during compile time, you can specify the size of shared memory directly at the declaration of shared variable. In case this information is not known, we dynamically figure out the amount of shared memory during runtime and declare this information from outside kernel, therefore keyword extern. Third argument of kernel launch, together with blocks, threads within each block, is amount of shared memory per block. In case of shared memory reduction, we need to load data from global memory to our declared shared array. We need to synchronize threads after this operation. Let's say that two threads, thread 1 and thread 2, each load a data element from global memory and store it to shared memory. Then, first thread wants to read second element from shared memory. Let's assume that our two threads are threads in different warps. If second thread has not finished writing its element before the first thread tries to read it, we have a race condition. which can lead to undefined behavior and incorrect results. Sync thread barrier ensures that threads proceed to reduction for cycle only after the shared memory has been loaded from global memory. In order to efficiently use the data from shared memory, it should be reused many times. Otherwise, there is no performance benefit, since the data first need to be loaded from slow global memory and later written back. Our application will be efficient only for big iteration variable, that is, for big thread block size. And after we finish the reduction, we need to write the reduction result back to global memory, so that it can be further proceed in case of partial per block results, or transferred back to host after the reduction is complete. This is the demo program where we want to reduce 130 million integers. We will compare performance of reduction using a global and shared memory. For Tesla K20, the global memory reduction took 54 milliseconds, while the shared memory took only 49 milliseconds. You might get different numbers depending on the used device, its architecture, and some other factors. Here we have our shared memory reduction kernel we have already seen. We create shared memory, initialize it by loading data from global memory, and after the reduction is complete, we write the result back to global memory. Global memory reduction kernel is rather straightforward, basically the same code without the shared memory. In the main function, we see standard procedure of any application. We allocate memory to hold our data. Memory is initialized to 1 so that we can easily verify the result. What is worth mentioning is that the result of calling the reduction kernel is not a single number, but a array of partial results. For every thread block, we get one reduction result, which we need to further process in case we run our kernel with multiple thread blocks. Therefore, we repeat our kernel launch until we run it only with a single block, which will produce the final result. The CUDA events are used to measure the elapsed time of the reduction. Basically, we mark two places in the code with CUDA event record, and then compute the time difference between these places, which will get us the execution time of the given code block. If we run our reduction kernel with block size of 512 threads, we can compare the execution time of both kernels. We see similar numbers as we have seen before. We see some speed up, so it is really beneficial to use shared memory in case of kernels with high memory access and a high data reuse ratio. In this particular reduction, there could be done more optimizations, such as coalescing memory, removing divergent branching, thread idling, or loop unrolling. However, even with this simple optimization of memory access pattern, we see some speed up. To achieve high memory bandwidth for concurrent accesses, shared memory is divided into equally sized memory modules, banks, that can be accessed simultaneously. However, if multiple threads requested addresses map to the same memory bank, the accesses are serialized. The hardware splits a conflicting memory request into as many separate conflict-free requests as necessary, decreasing the effective bandwidth by a factor equal to the number of colliding memory requests. Shared memory banks are organized such that successive 32-bit words are assigned to successive banks. Each bank can service one address per cycle, so that shared memory can service as many simultaneous accesses as it has banks. For devices of compute capability 1, the warp size is 32 threads and the number of banks is 16. A shared memory request for a warp is split into two requests. For devices of compute capability 2, the warp size is 32 threads and the number of banks is also 32. Therefore, a whole warp can be serviced in one request. Devices of compute capability 3 have configurable bank size, which can be set to either 4 or 8 bytes. Setting the bank size to 8 bytes can help to avoid shared memory bank conflicts when accessing double precision data. In the left use case scenario, different threads are accessing different banks, therefore there are no conflicts. In the other use case, first 4 threads are accessing the same memory bank, which will result into conflict and serializing requests into 4 consecutive memory accesses. Exception to the bank conflict is broadcast when all threads from warp request read operation from the same bank, resulting into memory broadcast. Another exception is when multiple threads request the read from the same memory bank, which will result into multicast. This optimization was introduced in Fermi Architecture. This concludes our part on shared memory. Next part we will have a look on efficient data transfers. In this part we will talk about efficient data transfers between host and device or between multiple devices. We will see properties and implementation of PCI Express communication bus and how various memory types influence transfer bandwidth and latency. We will have a closer look on performance of unified virtual memory, which was introduced in CUDA 6 and supported since Kepler Architecture. In the last part of this data transfer section, we will introduce CUDA streams that are necessary in order to utilize parallel data transfers. It is important to understand what impact does data transfers have on overall application performance. In this setting, we have CPU and GPU, each having its own memory space with solid memory bandwidth. Obviously, the weakest link is the interconnection between CPU and GPU. PCI Express of second generation provides bandwidth of 8 GB per second in ideal case. But we will see that actual bandwidth may be even lower depending on the overall architecture of the compute node. You will learn properties and some good practices regarding the host-device data transfers. It is useful to realize when the data transfers between CPU and GPU are performed. Obvious answer is that data transfers are performed when transferring input and output arrays between CPU and GPU. But there are more events that involve communication. First of all, it is transfer of binary code to GPU, passing kernel arguments such as block size or amount of shared memory. Communication is also performed when transferring return variables or initializing device variables. PCI Express is computer expansion bus that provides point-to-point connection on logical level. Each logical interconnection consists of multiple lanes, and when there are multiple processes requesting PCI lanes allocation at the same time, total amount of lines is divided between processes, which limits the effective bandwidth per process. Single PCI lane is full duplex line with transfer rate of 500 MB per second in both directions. PCI Express of second generation can assign maximum of 16 lanes with peak transfer rate of 8 GB per second. We have seen that Kepler and Maxwell architectures are using PCI Express of third generation that doubles the peak bandwidth of previous second generation. The next gen PCI Express bus has been already announced with release date in late 2015. It will double the performance of the current PCI Express generation, reaching bandwidth 31 GB per second. Also, this is the Tesla GPU, and this part over here are the PCI Express pins that allows the GPU to be connected to the host system. This is the result of PCI bandwidth test, where packets of different size are transferred over PCI. It is important to realize that we reach full bandwidth only from some reasonable size of transfer data. Reasonable bandwidth is reached from the data size of approximately 500 kilobytes. Therefore, it is better to pack all data into one package and send all at once, rather than sending individual small chunks of data between host and device. In this test, we also see performance difference between regular memory, depicted in blue, and pinned memory in red. We will discuss properties of these memories in the following part. PCI Express is shared between multiple peripheral devices and multiple processes, so the effective transfer rate varies depending on the PCI lane's availability for our process. We see that in one case, our process gets allocated 9 lanes, reaching bandwidth of 4.5 GB per second. And at some point, it gets guaranteed extra 3 lanes, summing up to 6 GB per second bandwidth. You cannot influence this behavior as the application programmer, but you should be aware of this, especially in case you will be building your own GPU cluster. So you already know that CPU and GPU have their own physical memory spaces, as well as different GPUs have their own global memories. That means we have to migrate our data between the nodes as necessary using the weak PCI Express link. In the following part, we will inspect various data transfer types and see if there is some possibility how to boost performance of these data transfers. So we will discuss following data transfer types. First of all, it is pageable and pinned or page-locked memory transfers. Then we will see explicit and implicit data transfers. We will also inspect the performance of the unified virtual memory. We will have a look on data transfers between GPUs within the same host and GPU communication over the network interface. And finally, we will inspect non-blocking asynchronous data transfers. First of all, let's have a look on the difference between pageable and pinned memory. When you allocate memory in a host code, the allocations are pageable by default, which means it may be swept to disk. So your data may not be present in a physical memory when the transfer to device is requested. On the other hand, pinned memory is allocated within the kernel memory space, depicted as this part of memory space, which cannot be swept, therefore such data are always physically present in the memory. When a regular memory transfer is issued, an allocation of page-locked memory is necessary, followed by a host copy from regular memory to the page-locked one. Afterwards, the transfer takes place, host is blocked and waits for the transfer to be completed, and then performs the deletion of the page-locked memory. This consumes host time, which is avoided when directly using page-locked memory. Please note that the GPU memory is automatically allocated as page-locked, since the GPU memory does not support swapping to disk. There is no need to do any special memory allocations like in CPU case. In our PCI Express bandwidth benchmark, you can see that pinned memory transfers achieve higher peak transfer rate than a transfer rate of regular memory. In general, this is because we avoid additional implicit mem copies within the host memory. We also have more realistic benchmark, a simple stencil code that computes wave propagation. Basically, it contains 4 core activities, that is transfer of data from host to device, kernel compute, backward data transfer to host, and some finalization of computation on host. In this case, we used regular memory, and in the other case, we used pinned memory for data transfers. Also, in this benchmark, we observe slightly better performance, especially of transfer from host to device. Pinned host memory can be allocated by API function CUDA malloc host, as opposed to regular host memory allocation using standard C function malloc. CUDA malloc host takes 2 arguments. It takes size of the requested memory and returns pointer to allocated memory, similar as CUDA malloc that allocates memory on the device. Take-home message about pinned memory should be that it usually performs better as regular host memory. We have seen that in both benchmarks we have reached a higher bandwidth of data transfers. However, you should not over-allocate pinned memory, since it reduces amount of physical memory available for kernel of the operating system. In such cases, the system could become unstable. In this part, we will inspect performance of the unified virtual memory introduced in CUDA 6. Unified virtual memory is an abstraction of host and device memory on programming level. Developer views the memory as if there is only one shared memory between host and device. On the hardware level, there are of course two distinct memory spaces, as we have seen in previous sections. Unified virtual memory simplifies developing or porting of your applications to CUDA. As you see, without the unified virtual memory abstractions, you explicitly need to declare two distinct memory spaces for your data and manually manage all the data migration between host and device. In case of unified virtual memory, all these transfers are managed by CUDA engine. You can request for virtual memory by API function CUDA malloc managed and use the memory in kernels or in host functions as needed. Let's inspect the performance of this memory feature in CUDA. Let's assume the use case where we want to load and initialize data on host, use it in GPU kernel to compute wave propagation stencil code, and finalize the computation on host to compute some statistical properties. This will require two data transfers. First, host to device transfer, followed by kernel launch, backward device host transfer, and finally the host computation. We have already seen the performance of this application using explicit data transfers with regular and pinned memory. The performance of virtual memory is significantly degraded. This is because the data migration, managed by the CUDA engine, is performed in multiple smaller transfers when data are accessed from host. This introduces a lot of latency and also achieves poor bandwidth. That's why the blue portion of the figure, corresponding to device to host transfers, is so much greater than explicit memory transfers, where the data are transferred all at once. Performance of the virtual memory in the other direction, that is host to device, is comparable with explicit memory transfers, since we do not observe this problematic behavior. However, the unified virtual memory still performs better than old memory mapping system known as zero-copy memory. In this case, memory is always present in the pinned host memory. If kernel uses such memory and requests access to some portion of it, data are always transferred from host, even if requested multiple times from kernel. One further performance issue with unified virtual memory is that it implements critical section to access memory. In case we use multi-threaded host application, the threads requests to access memory are serialized, resulting into performance degradation. In case of serial CPU code, UVM is 1.7 times slower, but in case of multi-threaded code, the UVM is 4.5 times slower than explicit memory. To sum up this section, the unified virtual memory simplifies programming model, but has performance issues in case of device to host transfers and in case of multi-threaded applications. However, it is still good in a sense that it simplifies GPU porting, allowing you to omit explicit memory copies during intensive GPU kernel code development. Following part will discuss peer-to-peer data transfers. Peer-to-peer data transfer is transfer between two devices located within the same shared memory server, so that communication can be performed over PCI Express and not going through network interface. Peer-to-peer allows us to copy data directly from GPU 0 to GPU 1 without allocating and staging memory for host. Peer-to-peer data transfer thus reaches high bandwidth that saturates PCI bus. Without peer-to-peer technology, we would have to first copy data from GPU 0 to host, and only from host copy it to target GPU. Another feature possible thanks to peer-to-peer is direct access. We can access data located in a GPU 1's memory from kernel running on GPU 0, without explicitly copying data. Such data are cached in L2 cache on the target GPU, in this case that would be GPU 0. Peer-to-peer feature is possible thanks to second generation of GPU Direct and unified virtual addressing. Unified virtual addressing was introduced in CUDA 4 and supported since Fermi Architecture. In a regular cluster node, we have devices connected to PCI Express, each having its own memory space. If we use data pointer in our code, which is basically some data address, it can physically exist in all memory spaces, either host memory or in one of the GPU's memories. In such case, we need to specify direction of the memory copy, the fourth parameter in CUDA memcopy, host to device, device to host, or device to device memcopy. With unified virtual addressing, all the addresses are mapped to a single address space. Note that individual memories are still physically separated, only logical memory addressing is continuous. In such case, we can do all our memcopies without specifying its direction, which will be identified automatically, since destination address can exist exactly once within the server. Here you see code of peer-to-peer transfer. In this example, we allocate some memory on both of our devices, enable peer-to-peer access, and copy data from GPU 0 to GPU 1. Note the last parameter in CUDA memcopy, that is CUDA memcopy default. Since CUDA engine can determine that GPU 0 buffer lies within the GPU 0 address space, and the GPU 1 buffer lies within the GPU 1 address space, we don't have to specify any more information regarding the direction of memcopy. You can also use this option instead of CUDA memcopy host to device or CUDA memcopy device to host, in case your server supports UVA. However, it is good programming practice to specify the transfer direction. To sum up, we have seen that peer-to-peer and a unified virtual addressing can be used to both simplify and accelerate CUDA programs. Unified virtual addressing maps all the memory addresses to a single address space, which enables CUDA engine to determine physical memory location from pointer value. It simplifies library interface, for example CUDA memcopy, and enables us to copy data between GPUs with less overhead. That is, data can be copied directly from one device to another and not staged through host memory. Now let's have a look on communication between GPUs over the network interface. Second version of GPU Direct, together with Unified Virtual Addressing feature, allowed to implement peer-to-peer data transfers. It used high-speed direct memory access transfers to copy data between the memories of the two GPUs within the same node. Third generation of GPU Direct uses remote direct memory access transfers between GPUs and other PCI devices. That enables us to send data between GPUs on different cluster nodes. Consider we want to transfer data from one GPU to target GPU located within a different network node. Without GPU Direct feature, data would be transferred first to CPU memory of current node, then to driver memory of network card. Data would be sent over interconnection network to network card controller of node 1, copied to memory of host in target node, and only from there transferred to memory of target GPU. GPU Direct eliminates unnecessary system memory copies, dramatically lowers CPU overhead, and reduces latency, resulting in significant performance improvements in data transfers. GPU Direct is also an essential requirement to utilize CUDA-aware MPI. In previous two sections, you have seen that efficient data transfers could be achieved by using write technologies. However, in some cases, using write underlying technology isn't just enough. You also need to use write programming features. One of such are asynchronous data transfers that enables you, for example, to hide communication latency by overlapping communication by computation. Regular CUDA memcopy is blocking, so it will block host until the transfer is complete. On the other hand, asynchronous CUDA memcopy is not blocking, so that the return from this function is immediate, and you can utilize CPU with some useful computation while data are being transferred. There are two additional requirements for asynchronous memcopy. First is that the transferred memory has to be allocated as pinned, so that no page faults occur during the transfer, and the whole transfer can be realized using DMA feature independently on the CPU. Second is that you need to specify CUDA stream. Basically, stream ID is just a number that specifies sequence of some CUDA operations. Operations from different streams can be performed in parallel. Since the asynchronous memory transfers are non-blocking with respect to host, CPU can use its time more efficiently, rather than idling in case of synchronous data transfers. CPU can issue the memcopies and kernel call, and while data are being transferred, or kernel is running its computation, CPU can use all this time to compute something useful. In case with used blocking memory copies, only the kernel call is asynchronous with respect to host, so only this portion could be overlapped. There is no speedup when compared to blocking data transfers. We only utilized CPU. With asynchronous data transfers, it is possible to overlap communication and computation, as you can see here. Using this technique, you can actually achieve some speedup. But in order to write this code, we first need to introduce CUDA streams. Here you see basic example of asynchronous data transfer. We allocate pinned host memory with CUDA malloc host and pass this data to CUDA memcopy async. CPU issues these three operations in asynchronous manner. So while the memory is being transferred or kernel is being computing, CPU can continue its own computation, in this example in function f. CPU will get blocked only on CUDA device synchronize, which will block until all previously issued GPU operations are not finished. Here you also see stream ID, which is the last parameter of CUDA memcopy async, as well as the last parameter of the kernel call. In this example we used default null stream. Let's get back to our example and see how you can overlap communication with computation. You can do this using CUDA streams. Stream is a sequence of CUDA operations that execute in issue order on the GPU. You might not be aware of that, but you have already used CUDA streams. If you don't specify CUDA stream explicitly, all CUDA operations are put to default, so-called null stream. For example, regular CUDA memcopy or kernel launch without specified stream. That's why CUDA memcopy will execute only after kernel that computes data to be transferred, even though kernel launch is always asynchronous. These operations are located within the same default stream, and from definition of CUDA stream, operations execute in issue order within single stream, even though kernel launch is asynchronous with respect to host. Therefore, if you put different CUDA operations to different streams, they may run concurrently. And this is exactly how we achieve the memory latency hiding by overlapping it with computation. This is a simple demonstration of the asynchronous CUDA memory transfers and usage of CUDA streams. First of all, you need to create the streams. In this code example, we create two streams using CUDA stream create function. What you need to do next is submit work to these streams. CUDA memcopy async takes stream identifier as last fourth parameter. CUDA kernel launch similarly takes stream identifier as fourth parameter. First two are well-known number of blocks and threads within each block. Third parameter is amount of shared memory per block, and last parameter is stream ID. Operations in one stream will execute independently of the operation in the second stream. At the end, you should not forget to destroy the streams and free related memory. When the work has been submitted to CUDA streams, CPU can run its own computation independently on GPU, in parallel with operations from both streams. Only CUDA device synchronize will block until all the GPU operations are not finished. There are cases when you need to synchronize operations within different streams. CUDA offers you multiple levels of control. CUDA device synchronize blocks until all previously issued operations within all CUDA streams for given GPU are finished. CUDA stream synchronize blocks until all previously issued operations from given stream are finished. And finally, fine-grained synchronization is provided by CUDA events. Stream 2, identified by CUDA stream wait event, will be blocked until stream 1, specified by CUDA event record, reaches the given event. Event is basically an empty operation in some stream, which can be used for synchronizations or for measuring execution times and so on. Following operations are implicitly synchronized, therefore no barrier is needed. All these operations have the same effect as CUDA device synchronize. To conclude this section of efficient data transfers, we have seen how does PCI Express work, that it can be shared by multiple users or processes, and therefore the peak bandwidth gets limited. We have also seen that PCI Express is efficient, only starting from some reasonably large data buffer. In the next part, we have inspected performance of the unified virtual memory. It simplifies programming model and may be convenient to use it during rapid porting to CUDA, but its performance may be worse, especially in case of device-to-host transfers, where data are transferred in small chunks. It's always a good idea to know when underlying runtime routes data through intermediate buffer and avoid it. For example, by using pinned memory or deploying GPU direct technology in your server. And the last point, regarding the asynchronous memory transfers, is that it's always a good idea to compute something while data is being transferred. In this way, you can efficiently hide memory latency in your applications. In the last part of this webinar, we will inspect profiling tools that are especially useful when optimizing your applications and you need to discover the bottlenecks and the most time-consuming operations. We will also have a look on two debugging tools, that is CUDA GTB and CUDA memcheck.